sampling distribution of a sample proportion. So just as the sample mean x bar has a sampling distribution with a mean and a standard deviation, the sample proportion p hat also has a standard sampling distribution with a mean and a standard deviation. What does this distribution of p hat look like? So recall the binomial distribution. Let x be a binomial random variable. X corresponds to how many successes out of n. P hat corresponds to the proportion of successes out of n. So if we have a case where, let's say, n equals 4 and p equals 0.3, we can find the probability of x equal to each of these specific values, right? The probability of 0 successes, 0.24, the probability of 1 success is 0.412, etc. And so we have the number of friends who develop a severe lung condition, right? So our xi, right, could be 0 through 4, and so we can have probabilities for each of these values 0 through 4. But we can turn this x into a p hat just by dividing by n. So we can make this, instead of being the number of smoking friends who develop a severe lung condition, we can make this the proportion of smoking friends who develop a severe lung condition. Instead of making it 0, 1, 2, 3, 4, it's now 0 out of 4, 1/4, 2/4, 3/4, 4/4. And the distribution of p hat is identical to the distribution of a binomial random variable x. It's just a change of scale. Since we divide by n to get from binomial random variable to p hat, we find the mean and the standard deviation of p hat by starting with the mean and standard deviation of x and dividing by n. So remember that the mean of a binomial random variable is n times p. If we divide that by n, we're going to get that the mean of the sampling distribution of p hat is equal to the true population proportion p. And this makes sense because the sample proportion is an unbiased estimator of the population proportion. The mean of the sampling distribution is equal to the population parameter that we're estimating. The standard deviation of the sample proportion, right? Remember, the standard deviation of a binomial is the square root of n times p times 1 minus p. We divide that by n, we can make that p times 1 minus p over n and square root it. So as the sample size n increases, the variability in the sample proportion, as well as the sample mean, goes down by the square root of n, just like with our sampling distribution for a mean. So mean and standard deviation for a sample proportion. How large does n need to be for the sampling distribution of p hat to be approximately normal? The sample size is considered large enough if the expected number of successes and failures are both at least 10. So NP at least 10 and N1 minus P at least 10. You'll have to check both of them. So here are 4 pairs of binomial distribution parameters, which distribution can be approximated by the normal distribution. So NP is 95, but N1 minus P is only 5. So that doesn't work. Here, NP is 11.25, and N times 1 minus P is 13.75. So this can be approximated by the normal distribution. Here, NP is going to be 7.5. And I think NP is the same here. So you multiply N by 5, but you divide. And it's not quite the same. You multiply N by something. It's the same, about the same. But 2 is the only one where the distribution can be approximated by the normal distribution. Because both NP and N1 minus P are both equal, are both greater than 10, or at least 10. What is the probability that the average Facebook user with 245 friends has 70 or more friends who would be considered power users? Approximately 25% of Facebook users are power users. So, right, the probability of being a power user is 0.25. The mean of this distribution, the average user is going to have 61.25 friends who are power users with a standard deviation of 6.8. And what we did is we found the probability, since NP and N1 minus P are both at least 10, we could approximate this using the normal distribution. And we found the probability that, we could do normal CDF with a lower bound of 70, an upper bound of 1E99, a mean of 61.25, and a standard deviation of 6.78, and that should give us this. They did it by finding the z-score first. That's also fine. So this is the probability of a single person. A single person who has 245 friends has 70 or more who could be power users. But we can do the same thing using the sample proportion p hat. So the average Facebook user with 245 friends, when you already verified the conditions, but 70 out of 245 would be 0.286. And our mean is going to be 0.25. Our standard deviation is going to be 0.028. And if we calculate the z-score is the same as it was back here, which means that we're going to get the same proportion. Or you could do normal, same percentage, or we could do normal CDF with a lower bound of 0.286, upper bound of 1E99, mean of 0.25, standard deviation of 0.028. And that should give you the same thing. So, given a population that is 50% people of color, what is the probability that a sample size 200 would have greater than 55% people of color? Remember to verify the conditions. So, NP is 100, right? Our N is 200, our P is 0.5, and 1 minus P, also 100. That satisfies the large counts condition. So this distribution is going to have a mean equal to P, which is 0.5, and a standard deviation equal to the square root of P times 1 minus P over N, which is 0.5 times 0.5 over 200, and take the square root of that. Which comes out to be 0.035. So we could do our normal CDF with a mean of, or with a lower bound of 0.55, an upper bound of 1E99, a mean of 0.5, and a standard deviation of 0.035. All right, and if we sketch that, all right, we have verified that we can approximate using the normal distribution. So a mean of 0.5, we want 0.55 or higher, so we want this. And that's going to turn out to be 0.07, about 7%. All right, our mean is 0.5, it's equal to P. This is the standard deviation that we calculated. You can find the z-score, or you can just plug it into the normal CDF. And that's it. Proportions are pretty simple.